Welcome students, I am Dr. Rajesh Singh and in this video we will solve exercise for section 4.3 from the book Bartle and Sherbert. So let us start with the question number 1. We have to prove theorem 4.3.2, which is the sequential criteria for one-sided limits. So we have to show that limit x tends to c positive f is equal to L if and only if for every sequence xn that converges to c with xn greater than c, the corresponding sequence fxn must converge to L. So let us start writing the proof. So we will first prove 1 implies 2. So for this we will assume that limit x tends to c positive f is equal to L, and let xn be any sequence in A intersection c to infinity such that xn converges to c. So we have to show the corresponding sequence fxn converges to L. So this is what we have to show. So what we will do, we will take any epsilon greater than 0. So let epsilon greater than 0 be any real number. So we have to find some m belonging to z positive such that fxn minus L should be less than epsilon for all n greater than equal to m. So we will use this. So what we will do, we will use this fact for this epsilon. So since limit x tends to c positive f is equal to L, so for epsilon greater than 0 there exists delta greater than 0 such that 0 less than x minus c less than delta implies fx minus L is less than epsilon. So this is our star. So now we will use, for this delta we will use the sequential condition. So since xn converges to c, so for delta greater than 0, so instead of epsilon I am taking delta. So for delta greater than 0 there exists m belonging to z positive such that xn minus c is less than delta for all n greater than equal to m. Now since xn is greater than c for every n, so what this implies, I can remove this mod and I can write it like this: xn minus c is, so this mod is not here, so this mod is not here, so xn minus c is less than delta for all n greater than equal to m. So mark this as double star. Now using double star and in star, so using double star in star, because all these xn satisfies this condition, xn minus c is less than delta, so fxn minus L should be less than epsilon. So using this we get for all n greater than equal to m, 0 is less than xn minus c less than delta, so this implies fxn minus L is less than epsilon. So this is what we wanted to prove. Hence limit n tends to infinity fxn is equal to L or fxn converges to L. So this is what we had to prove. Now converse part we will do second implies 1. So for that, so now we will prove second implies 1. So suppose second is true. To show what we have to show, that limit x tends to c positive f is equal to L. So suppose we will take the contrapositive approach. So suppose on the contrary limit x tends to C positive, f is not equal to L. So what does this mean? We will take the negation of the definition of limit x tends to C, f equal to L. So what is the definition? Let us first write the definition. So what is the definition? The definition is limit x tends to C positive, f is equal to L if and only if for each epsilon greater than 0 there exists delta greater than 0 such that for all x with 0 less than x minus C less than delta, this should imply fx minus L is less than epsilon. So now what? So let us try to negate this statement. So what should be the negation? So to negate, what you will do, you will write, so suppose limit x tends to C, f is not equal to L. So this is equivalent to saying each will become there exists. So there exists epsilon greater than 0 such that this will become for every delta greater than 0. So this there exists will become for each delta greater than 0 such that for all will become there exists x, and this will depend on the choice of delta with 0 less than x minus C less than delta, but this will not hold. So that is fx minus L will be greater than epsilon. So let us write the statement. So this implies there exists epsilon greater than 0 such that for any delta greater than 0 there exists x depending on delta belonging to A intersection C to infinity such that 0 is less than x delta minus C less than delta, but fx delta minus L is greater than epsilon. So this is greater than epsilon. Fx delta minus L is greater than epsilon. So what we will do, since this is true for any delta greater than 0, so we will take delta equal to 1, and then for that we will get 1x1, then we will take delta equal to 1 by 2 and we will get x2, then we will take delta equal to 1 by 3, we will get x3. So on we will proceed inductively and we will construct a sequence xn such that xn minus C is less than delta for all n belonging to n. So this is what we are going to do. So for each n belonging to n, for delta n equal to 1 by n, there exists xn belonging to A intersection C to infinity such that such that 0 is less than xn minus C is less than 1 by n delta n, or you can write delta n, but fxn minus L is greater than epsilon, and this is true for all n belonging to n. So this implies, thus we have constructed a sequence xn in A intersection C to infinity such that xn converges to C, but fxn minus L is greater than epsilon for all n belonging to n. That is, fxn does not converge to L, which is contradiction to second condition. Hence, our assumption that limit x tends to c positive f is not equal to L is wrong. Thus, limit x tends to c positive f is equal to L. So this completes the proof of question number 1. So let us move to the question number 2. So in question number 2, we have to give an example of a function that has a right hand limit but not a left hand limit. So this is simple. We will take fx equal to 0 if x is greater than or equal to 0, and 1 by x if x is less than 0. We have already shown that limit x tends to 0 negative f of x does not exist. So you can see the proof in one of my videos, so I'm not going to do it here. Then limit x tends to 0 negative fx does not exist, but limit x tends to 0 positive f of x is equal to 0. So this is constant when x is greater than or equal to 0. So when we will approach from the right, we will get 0 as the limit, and this becomes unbounded when x approaches from 0 from the left. So limit at left hand point does not exist, while limit at right hand point is equal to 0. So we have found a function example of a function such that limit x tends to 0 negative fx does not exist, but limit x tends to 0 positive fx exists. So this you can prove yourself. It is there in one of my videos, so you can watch it there also. Now let us move to the question number 3. So in question number 3, we have been given that fx. So what we are given fx is equal to 1 by root mod x when for all x not equal to 0. So this is what we are given. We have to show limit x tends to 0 positive f of x is equal to limit x tends to 0 negative f of x is equal to plus infinity. So we will start the proof by proving that. So we will first prove that limit x tends to 0 positive fx is equal to plus infinity. So for this, what we will do, we will take let k greater than 0 be any real number. So we have to show there exists delta greater than 0 such that 0 less than x minus 0 less than delta should imply fx is greater than k. So this we have to show. So we will start with consider for x greater than 0 fx greater than k. So this is equivalent to writing 1 by root mod x is greater than k. Now what we will do, we will square, since all the numbers are positive, so we can take the square on both sides and inequality will be preserved. So this becomes 1 by mod x greater than k square. So now we will take the reciprocal. So this is mod x less than 1 by k square. Now since x is positive, so I can write it as x less than 1 by k square. So I will, because this is what I wanted some delta such that x minus 0 less than delta should imply fx greater than k. So what I will do, I will take delta equal to this 1 by k square. So take delta equal to 1 by k square. Then 0 less than x minus 0 less than delta implies x is less than delta, and this implies x is less than 1 by k square, and from here we get this is equivalent to fx is greater than k, and this is what we wanted to prove. So hence limit x tends to 0 positive f of x is equal to plus infinity. So this proves the first limit. Now we will show another limit. Next we will show that limit x tends to 0 negative f of x is equal to plus infinity again. So for this again we take any k greater than 0, be any real number. So we have to show there exists delta greater than 0 such that 0 less than 0 minus x less than delta should imply fx greater than k. So consider for x, because this time we are approaching from the left, so I am taking x to be less than 0, fx greater than k. So this is equivalent to writing 1 by root mod x is greater than k. Since all the things are positive, I can take square on both sides. So 1 by mod x is greater than k square, and this is equivalent to writing mod x is less than 1 by k square. Now since x is less than 0, so this is equivalent to this minus x less than 1 by k square since x is less than 0. So this is what I wanted to prove. I wanted to find some delta such that minus x less than delta should imply fx greater than k. So minus x less than 1 by k square implies fx is greater than k. So I will take delta equal to 1 by k square, then 0 less than 0 minus x less than delta implies minus x is less than 1 by k square, and this is equivalent to writing fx is greater than k. Hence limit x tends to 0 negative f of x is also equal to plus infinity. So this completes question number 3. Now let us move to question number 4. So in question number 4, we have been given a point C in R and f is a function such that fx is greater than 0 for every x in C to infinity. We have to show that limit x tends to C, f is equal to infinity if and only if limit x tends to C 1 by f is equal to 0. So let us start the solution. Given is fx is greater than 0 for every x belonging to C to infinity. To show limit x tends to C, fx is equal to infinity if and only if limit x tends to C 1 by fx is equal to 0. So what we will do, we will first assume this and we will show this, then in the next case I will assume this and I will prove this. So first assume that limit x tends to C, fx is equal to infinity. So we have to show limit x tends to C 1 by fx is equal to 0. So because we have to show this to be 0, so we will take let epsilon greater than 0 be any real number. Then we have to show there exists delta greater than 0 such that 0 less than mod x minus c less than delta 1 by mod fx minus 0 is less than epsilon. So this is what I have to show. And since the domain of the function, since the function is defined on x to infinity, so I will have to take an additional condition that x belongs to C to infinity, and this is what I have to show. I am been given that limit x tends to C, fx is equal to infinity. So for any k there exists delta. So what k we should choose? We should take k equal to 1 by epsilon, because this epsilon represents small number and we want to have some, and k represents larger number. So we will take k equal to 1 by epsilon. So let k equal to 1 by epsilon greater than 0. Then as limit x tends to C, fx is equal to infinity, so there exists delta greater than 0 such that x belonging to C to infinity, because this is the domain, and 0 less than x minus c less than delta implies fx is greater than k. Now fx is greater than k is equivalent to writing, and is equivalent to writing 1 by fx is less than 1 by k, and which is epsilon. So this is equivalent to writing 1 by fx is less than epsilon. Now because x belongs to c to infinity, so fx is positive, so I can take this into mod and I can write these. Both the statements are equivalent because this x belongs to c to infinity and fx is given to be greater than 0 in x belongs to c to infinity. Fx is greater than 0 for all x belonging to c to infinity. So this is what we were to prove. This is the condition that we had to prove, that if x belongs to c to infinity and 0 is less than x minus c less than delta, then I should have 1 by fx minus 0 less than epsilon. So this is what I have proved, that if my x belongs to c to infinity and 0 is less than x minus c less than delta, then my 1 by fx minus 0 is less than epsilon. So hence limit x tends to c, 1 by fx is equal to 0. So this is the first part. Now we will prove the converse part. Conversely, assume that limit x tends to c, 1 by fx is equal to 0. So to show limit x tends to c, fx is equal to plus infinity. So I will take any k greater than 0, be any real number. So I have to show there exists delta greater than 0 such that x belonging to c to infinity, because this is the domain, and 0 less than x minus c less than delta should imply fx greater than k. So this is what I have to prove. So what now I have to use this fact, and for this I need one epsilon. So what epsilon I will take, because this k represents larger number and epsilon represents smaller number, so I will take epsilon equal to 1 by k. So let epsilon equal to 1 by k greater than 0, then as limit x tends to c, 1 by fx is equal to 0, so there exists delta greater than 0 such that 0 x belonging to c to infinity and 0 less than x minus c less than delta implies 1 by fx minus 0 is less than epsilon. So this is equivalent to writing, because x belongs to c to infinity, so fx is greater than 0, so I can write it like this. There is no need to have modulus because fx is greater than 0 whenever x belongs to c to infinity. So 1 by fx is less than epsilon, and this is equivalent to writing 1 by fx is less than 1 by k, because epsilon is equal to 1 by k, and this is equivalent to writing fx is greater than k. So hence we have shown existence of delta greater than 0 such that x belonging to c to infinity and 0 less than x minus c less than delta implies fx is greater than k. Thus limit x tends to c, fx is equal to infinity. So this is what we had to prove. Hence proved. So this completes question number 4. So in this video we will solve till here. In the next video I will solve question number 5 onwards. Stay tuned and subscribe to our YouTube channel for further updates. Thank you.